Thank you for kind introduction. Sawadika. Thank you for giving such a good opportunity of the presentation in KMPT. Actually, this is the first time for me visiting not only here but also in Thailand. I'm so excited now. Okay, before talking about the forward advanced technology, I would like to introduce my university and the institute. Thanks so much. That's fine? Okay. Kyushu University is located in the Fukuoka city. Fukuoka city is located in the Kyushu Island, the west side in Japan. Fukuoka city is very convenient to access from the Bangkok city. Because we have the direct flight from the Bangkok city to Fukuoka, the flight time is about 6 hours. The Fukuoka city is located in the Kyushu Island. This is the biggest city in the Kyushu Island. The population is about 1.6 million people. And the population is increasing now. Because Fukuoka city is very convenient, not only for residential, but also the sightseeing. Because there are so many historical places, and we can access to the ocean side and the mountain side. If you're interested in the Fukuoka city, please come. Okay. And Kyushu University has several campuses. The main campus is the Ito campus, slightly far from the center of the city. However, we have the baseball stadium for the national professional team in the Fukuoka Hawks. This is a very famous baseball team. My laboratory is not located in the main campus. The laboratory is located in another Kyushu campus. This campus is very convenient to access from the Fukuoka airport. Access time is about 1 hour by the public transportation. In addition, this campus remains the nature situation, so we can see the cherry blossom blooming in the spring and changing color leaves and in autumn, so that we can feel every time the Japanese four seasons. This is a brief history of the Kyushu University. The origin of the university is the medical school, and Kyoto Imperial University established the Fukuoka branch. This is the starting point of the Kyushu University. In 1911, the Kyushu Imperial University was established as the fourth Imperial University in Japan. The first one is the Tokyo University, the second one is the Kyoto, third one is the Tohoku, and the fourth one is the Kyushu Imperial University. This university started from mainly the medical department and the engineering, the medicine, agriculture, and so on. And then the faculty developed to the law, the literature, and science, and so on. After World War II, the university name changed to the Kyushu University, and then we have to continue for the higher education in Japan. This is the simple statistics in my university. The number of students is about 19,000 people. Actually the capacity of the Pepedon, the baseball stadium, is about 40,000. So our student can occupy the half of the baseball stadium. In addition, we have so many overseas students come from over the 100 countries and regions. The overseas student number is about 2,000. It's corresponding to the 30%. So if you are interested in our university, please come to the bachelor degree, and not only the bachelor degree, but also the graduate school, master course, and doctoral course. So, this is my institute. I belong to the Research Institute Applied Mechanics. As showing the research name, the starting point of the mechanical engineering, such as the fluid engineering and elasticity engineering. And then this is topics developed to the ocean research from the viewpoint of the waterfall and nuclear fusion, for the special materials, and the fundamental mechanics. Currently, the research topics mainly focus on the environment, not only the ocean side, but also the atmosphere from the viewpoint of the airflow. And nuclear fusion is a very hot topic at present, and the renewable energy also very important for the carbon neutrality. So my research is related with the energy conversion from the semiconductor point. My introduction already done by the person, so it can be skipped. And my knowledge member is not so huge. We have the 3 research fellows for the national project, and 2 doctoral students, and 5 doctoral students. So in my laboratory, we have the 3 main topics. The first one is the power device design and module designs for the device performance improvement. And the second one is the intelligent control, not only for the high performance, but also the additional new functionality. The final one is the reliability work, because the power device require high reliability for the safety operation. So at this point, I will present later. Okay, let's shift to the main talk. Today, this is the outline of my talk. Today, I'd like to talk about the power device technology trend. First, I'd like to talk about the brief history and the demand of the power devices. Then, I'd like to talk about the technology trend to answer the demand. And I'd like to talk about the outlook for considering with the future demand. Finally, I will conclude my talk. Okay, I talk about the power device. However, most people don't know what is power device. The power device is a kind of semiconductor device for the electric power control and energy conversion. For example, the energy grid, the transportation, and then industrial motors, recently the hot topics electric vehicle, and switching power supply from appliance. Also, usually we use for the energy charging in the smart mobile phone and so on. So if you don't know the power device, every day we use widely the power device. So the role of the power device is very simple, just a switch. However, why the simple switch can obtain the power control? This is the simple example. The switches, the symbol of the power device. In this case, this switch turns on, another one turns off. At that time, current flows this direction. At that time, electric energy can be stored in this inductor. After the switching, this device turns off, another one turns on. Current flow change to the straight direction. At that time, charge the energy transport to the secondary side. So this is the example of the power device operation for the energy control. So the energy flow can be controlled by the simple operation. However, the energy conversion and energy control requires high efficiency, low loss operation. So at the on state, the power device must be minimized, the conduction noise. So the on state resistance must be low. The switching operation also generates switching loss. So the high-speed switching is necessary for minimizing the switching loss. At the off state, the applied voltage must be sustained in the device, so high breakdown voltage is necessary for the safety operation. So the low resistance, high-speed switching, and high breakdown voltage are key factors, the main demand in the power device. So the power device is a kind of the semiconductor device, so the very similar the device structure and the fundamental physics is common with the logic device and memory devices. This is the cross-section structure of the power MOSFET. At the on state, the input gate signal applied to the gate terminal, the gate voltage is over to the higher than the threshold voltage. Immature layer is formed at the MOS interface, so the current path is formed in the device. At the whole state, the gate voltage becomes lower than the threshold voltage, so the immature layer disappears, and the deposition layer expands to sustain voltage. The switching operation can be obtained by applying the gate voltage signals. So the main physics is the same with the MOSFET device in the CMOS logic and so on. So this is the simple timeline of the power device history. At the first stage, the thyristor started the power device product. And then at the second stage, time control devices such as the GTO and the bipolar junction transistor, they became the main player. And then at the third stage, the MOSFET control device, the voltage control devices, they become the main player. And currently, we are starting at the fourth stage. The higher device performance are required, so the new devices, IGBT, silicon carbide, gallium nitride devices are developed. Okay, let's explain the detail of each stage. At the first stage, the first product, silicon control rectifier, SCR, was released in the 1957. So this is the beginning of the power device product. So the power device has about 70 years history. This is the beginning of the solid-state power conversion. So the power device opened the door of the power electronics application. However, the thyristor cannot turn off by themselves. So the application range is limited. So at the second stage, the current control device was necessary to expand the power electronics application range. So the main player shifted to the GTO and bipolar junction transistors. So however, the current control device can turn off However, the self-operating area is not so wide. So, as a next stage, in 1990s to the 2010s, voltage control device became a main player due to the easy to use of the MOSFET control and in the power MOSFET and IGBTs. So after that, the application area has been developed. Just now, at the host stage, the application engineers strongly requires more higher performance and more higher efficient system design. So the requirement becomes more complicated. So to answer this demand, the new devices and CIGBTs, the silicon carbide MOSFET, gallium nitride heads are developed. Especially the wide band gap material, such as the silicon carbide, gallium nitride, the focus from the application side, and because these materials have big potential for low loss operation. Because the material strongly related with the device design. The drift layer is the drift layer determines not only the on-state resistance but also the breakdown voltage. At the on-state, the vibration layer expands in the drift layer, and this electric distribution determines the breakdown voltage. So due to the critical electric field and the drift layer thickness, the higher electric field obtains thicker drift layer to keep the same breakdown voltage. Finally, the theoretical or resistance limit is determined by the cubic of the critical electric field. Usually, the wide band gap materials and the silicon carbide, gallium nitride have 10 times higher critical electric field compared with silicon. So the theoretical limit of the on resistance, they're quite low. They're about 1,000 lower than the silicon limit. This is the big motivation for the wide band gap device in the power device application. Okay, let's move to the next topic. I'd like to talk about the device technology trend. So the power device has answered for the power increase demand. So this is the typical demand in the power increase application. This graph shows the power density trend. The power density means the ratio between the output power and the system size. The power density has been increased continuously, 100 times higher for 30 years. So this trend shows not only the continuous increasing trend, but also this trend according to the various application. So it means this trend according to the common demand. It means cost reduction. So why the high power density operation obtains the cost reduction? It's a simple. The high power density operation means system downsizing. The small size shift obtains the small size materials and reduction of the components. So finally, the system cost can be reduced by a high power density operation. So at that time, how to determine the power electronic system size. This is the example of the power electronic system design. This is the example of the little box charge sponsored by the Google for the high power density operation. This photograph shows the size was system size mainly determined by the cooling component and the passive component. Not only this example, usually the power electronic system size determined by the 70 to 80% of the passive component and the cooling component. The cooling component is used for the cooling of the power device. So, low-loss operation of the power device is effective to minimize the cooling component. In addition, the switching frequency has a big impact for minimizing the passive component. So the high frequency operation is necessary. However, the switching loss in the power device increases with the switching frequency. So the high-speed switching is a key factor for the increasing the switching frequency. So from this scenario, the low-loss operation and the high-speed switching are key factor for the high power density operation. Then in addition, the priority of the demands strongly depends upon the leading application. This is the example of the driving holes of the impact application. In the 1980s to the 2000s, the driving force was the air conditioning. The market saturated. And then the new driving force has come. It was industry robot. And then this application also saturated. The new driving force has come. The recent hot topic, the electric vehicles. So every time the driving force are generated and technology was ready. So in the home appliance, such as the air conditioner, the refrigerator, and so on, this is the important point. The important point is the energy saving and to develop many equipment. So at that time, the robustness and the easy to use are important point. So the main player was shifted from bipolar transistor to the IGBT. And then the industry robot required the more small size for the lightweight of the system. So the high power density operation is very important. So the IGBT, the change to the field stop time for the power loss reduction. Recently, the electric vehicle demands the low-loss operation for the system downsizing and downsizing of the battery. So the RC-IGBT and silicon carbon MOSFET are suitable for this application. So every time the application side requires the cost reduction. So in the mass production, the high productivity is a very important factor. The power device is also the semiconductor device, as the same as the logic and the memory devices. So wafer diameter is a very important factor for the mass production. Also in the power device manufacturing, the wafer diameter was enlarged from the 4 inches, 5 inches, 6 inches, and recently the 200 millimeter wafers are used in the mass production, and recently the 300 millimeter production already started. And the fabrication technology are very important for the cost reduction and to increase the productivity. By early 1990s, the silicon process technology were big legacy from the CMOS logic and IC technologies. So the MOS gate structure can be easily produced, and ultra-fine structure is the big legacy for the improvement of the device performances. And then from the late 1990s and the 2010s, the special process technologies were required for the power device, such as the deep PM junction for the super junction structure, and very thin wafer process for the IGBTs. Recently, the power device product need not only the special process technology, but also the specific product line. So recently the 300 millimeter facilities are established, and also the silicon carbide and gallium nitride product line also built in the company. These are very big impact for the mass production, because the larger capital investment are required. So sometimes the company top management had a headache, how to increase the market share and how to reduce the development cost and so on. The 3mm silicon power device product started from the Infineon in Germany. And then the several companies followed the Infineon. Also in Japan, recently the several companies already started the 300 millimeter product. Also in the wide band gap, the power devices, the wafer diameter is a key factor for the mass production. At present, the 200 millimeter wafers are used for the mass production, and 300 millimeter wafers are already demonstrated in the R&D phase. Also in the wide bandgap device, the larger wafer diameter is effective to reduce the process cost for high productivity. However, the material cost is a key issue because it's very difficult to keep the crystal quality in the large size of the diameters. Okay, these are technology trends in the power device world. Next, I'd like to talk about the outlook for the future demand. So, as you know, we are facing the corner of the changing world. Several years ago, the information technology changed our society, such as internet, the personal computer, and mobile phone. Now, we are facing the new corner by the AI technology and the robotics. So we have to consider what change will be required in the power electronics and power device to answer the new society demand. The AI technology are very powerful tool and useful in our lives. However, the energy consumption that is increasing dramatically day by day. So, in the forecast, by the 2040s, energy consumption of the computer systems will reach to the global power generation. So, the AI technology are a powerful tool. However, the big risk for the energy consumption. So, how to reduce the energy consumption in the computer system is a very strong demand. And from the viewpoint of the power generation, carbon neutrality is a key factor. So the importance of the carbon neutrality becomes more and more seriously in the future. However, this is a big chance for the power electronics application. Because the power electronics application obtain not only the high efficiency, but also the renewable energy requires massive development of the power electronics application systems. Because, as you know, the power generation of the renewable energy is not stable. So, however, we need the stable power supply. So, the energy flow must be controlled by the power electronic systems in the future grid. So, the massive development of the power electronic systems are necessary in the future the energy grid. So, the high productivity of the power device has been required in the future. In addition, increase of the system become a risk of the increase of the failure rate. So, the high reliability is also important demand in the future. So I already say this is the big chance for the power application and power devices. Because new demand generate new device, such as, for example, the bidimensional switch is suitable for the microinverter circuit for PV application, and low-loss kinetic hand is suitable for the server system and power supply system. And the switch-state transformer require high voltage silicon carbide MOSFET due to the high-speed switching. And the DC grid demands solid-state circuit breaker for the safety operation. This application is suitable for the silicon carbide JFET due to the ultra-low resistance. So, the future demand, this is a big chance for the new power devices. However, the reliability is sometimes an obstacle for the mass production because the highly quality control is required. So we have to clarify the failure mechanism in the power device and packages. So, however, the silicon 300mm product line already has the big legacy from the silicon CMOS and memory mass production. Because production line has been already shifted to the digitalization. So the process feedback and the feedforward and the extraction order is impacting equipment, automation with the pattern defect detection. These are powerful tools for the high quality chip in the mass production. So the silicon power device they can be brought the high quality chip with low cost. On the other hand, the wide market device are starting in the different phase because the history of the mass production is different from the silicon power devices. Their history is quite short. So we have to start to correct what's happening in the device and how to control the crystal quality and mass production quality. So in the future, the wide gap devices are very attractive for the new demand. However, the quality control is a key issue in the mass production. In addition, and system side, also considering how to achieve the high reliable operation. We classified the safety operation level technology level 1 to level 4. Level 1 is the current phase. Usually system shut down before the failure by detecting the abnormal operation such as the high temperature, by the self-heating or after power reducing and so on. In the future, we have to step up in the more higher level technologies, such as level 2 in detecting the degradation by the monitoring to check the safety operation. The level 3 is the lifetime prediction to manage the maintenance timing. Finally, to expand the system lifetime, the shutdown prevention is necessary. So just now, we are studying the level 2 and level 3 technologies. So this is an example of my laboratory activity. These are related with the level 2 technology. The bonding wires lift off at the long time operation. So the switching waveform is useful to detect the change of the wire numbers. In our laboratory, using the AI technology, overanalyzing the switching waveform, the accuracy is achieved by the AI technologies. The other example is the measurement of the thermal resistance in the package. After the long time operation, the solder crack is occurred, and thermal resistance is increased. Finally, the chip temperature, easily to high, easy to rising. So finally, the device fail occur. So the measurement of the thermal resistance is important to detect the degradation. So from the gate voltage waveform, the junction temperature can be measured and detect the increase of the thermal resistance. Okay, let me conclude my talk. I talk about the progress in the power device technology. And in the history, device suited from the easy to use and higher performance to answer the application demand. This demand can be obtained by the low loss and high-speed switch operation for the hyper-density in the system. In addition, the device cost must be reduced, so the process technology and larger wafer diameter are key factor for mass production. In the future, the high productivity will be required continuously. And in addition, the new demand will generate the big channels for the biodynamic devices for the grid control. In addition, the massive development of the power efficiency system require high reliability. So the quality control and new technologies are the important point in the R&D. So about I already published the review paper related with today's topics. In the FX review paper, this is the open access paper, so that you can download it from the website. If you have interest, please download it. Okay, my talk is over. Thank you for your attention.